Hi, we are from Group 2 and today we're going to be presenting about Chapter 6, Reactor Scale-Up. So as for the topic outcome, we will be learning about the suitable criterion when scaling up reactors. Okay, so why do we need to learn this? Well, a fermentation that works well in a small reactor may not work the same way in a large reactor. And that is because the cell experience different conditions when the reactor becomes bigger. For example, oxygen may not reach all parts of the reactor properly, mixing becomes harder, heat removal becomes harder, or foaming and cleaning becomes more difficult. Okay, now for the introduction part. There are 7 steps in bioprocessing operation, but the step that requires effort for scale up is fermentation. Because oxygen transfer, mixing, heat transfer, and cell growth must still work properly in a large bioreactor. Inoculum and pre-fermentation steps also need some scale up to prepare enough healthy cells. So moving on to bioprocessing operation. In bioprocessing, the process starts by choosing and preserving the right strain. Then the cells are grown as inoculum and prepared before fermentation. During fermentation, the cells produce the bioproduct. After that, the product is recovered and purified, while the remaining waste is treated safely. Now moving on to scale up. Scale up means moving from a small lab scale bioreactor to a larger industrial scale bioreactor for commercialization. The goal is to produce the same bioproduct but in a much larger amount. However, we cannot simply increase the size randomly. We need to choose an ideal scale-up criterion, which means keeping an important parameter the same as the reactor size increases, which basically translates to having a constant as a parameter. Okay, so for the first scale-up criterion is the geometrical similarity. This means keeping the same shape by maintaining the liquid height to tank diameter ratio from lab scale to pilot and commercial scale. Well, that's all from me. Thank you.
In these sections, I will explain the scale-up problem in bioreactors. When a fermentation process is transferred from a small laboratory bioreactor to a larger industrial bioreactor, it is impossible to maintain exactly the same physical conditions while only preserving geometric similarity, which means keeping the same height to diameter ratio. As the reactor size increases, the surface to volume ratio decreases significantly. This creates challenges because less oxygen can enter the culture medium through surface aeration, while the removal of dissolved carbon dioxide becomes less efficient. As a result, the microorganism experience a different physical environment compared to the small-scale reactor. These changes can affect cell behavior and make the process performance difficult to predict. Several important responses may be affected, including the growth rate of the microorganisms, the amount of product formed, and the production of unwanted contaminating byproducts. Therefore, scale-up is not simply making the reactor bigger, but ensuring the biological performance remains consistent at a larger scale. To overcome scale-up problems, several important factors must be considered. The first factor is a mass transfer rate, especially oxygen transfer for aerobic microorganisms. Adequate oxygen supply is essential for cell growth and product formation. The second factor is mixing. Proper mixing ensures that nutrients, oxygens, and temperature are evenly distributed throughout the reactor. Heat transfer rate is also important because microorganisms generate heat during fermentations. Efficient heat removal is required to maintain the optimum temperature. Sterilizations must be carefully designed to prevent contamination when operating large-scale systems. Mechanical design is another important consideration because larger reactors experience greater mechanical stress and require stronger equipment. In addition, foaming can become a serious issue during fermentation. Excessive foam may cause contamination risks and operational problems. Finally, cleaning procedures must be effective to ensure product quality and maintain hygienic conditions between production batches. Among all these factors, oxygen mass transfer is often the most critical. Therefore, aerations and agitation systems are commonly optimized during scale-up to improve oxygen transfer efficiency throughout the bioreactor. In summary, reactor scale-up presents many challenges because the physical conditions change as reactor size increase. Therefore, factors such as oxygen transfer, mixing, heat transfer, sterilizations, mechanical design, foaming, and cleaning must be carefully controlled to ensure successful large-scale fermentation.
Now we go to the scaled up methods.
The scaled-down method always depend of the type of microorganism or behavior. For example, it's like shear-sensitive organism and aerobic organism. Aerobic systems such as yeast or E. coli fermentation, our most critical method is keeping the volumetric mass transfer coefficient or KLA in constant. This ensures that even in a 10,000 liter tank, every single cell receives the same concentration of dissolved oxygen as it did in the laboratory. If oxygen level drop, we risk metabolic shift and lower yield. Next, we have the power per unit volume basis. This is mechanical approach where we ensure the energy distribution rate is identical, while it's excellent for ensuring nutrient distribution in large industrial setting. Is often used in combination with other methods because maintaining the same can lead to extremely high impeller speed in small reactor. When dealing with biopharmaceutical like monoclonal antibodies, we use mammalian cells. These cells are fragile because they lack a cell wall. In this case, we scale up based on constant impeller tick speed by limiting the velocity at the very edge of impeller. We protect this sensitive cell from mechanical shear damage while still providing the necessary mixing. Lastly, we consider the Reynolds number. This is our go-to method when heat transfer is the biggest priority. Large-scale fermentation are highly exothermic. They generate a lot of heat by keeping the Reynolds constant. We ensure the flow patterns and turbulence are optimized for heat removal through the cooling jacket, preventing the bioreactor from overheating. The scale-up decision metric as always depend on biological targets like aerobic microbe, mammalian cells, general mixing, and thermophiles to keep their titration and also key advantage like in the tables. Thanks, that's all from me.
So now let's move to the scale down reactor. So scale down reactor is actually a smaller reactor that is mainly used for research and testing. It allows researchers to test many parameters faster and at a lower cost compared to the large scale system. For example, we can study the effect of changing the medium composition using different strain or adding new antifoam agent. From this, we can observe the system response such as growth rate and product formation. So beside that, scale down reactor also help identify problem early, such as pH probe or oxygen supply failure before applying the process to the large scale production. So overall, it is a practical and efficient system for process development. So next is the key differences between scale up and scale down reactor. So this table compare both of the reactor. So scale up reactor are mainly used for mass production, while the scale down reactor are more suitable for testing and simulation. In terms of cost, scale up reactor require larger equipment, more space, and higher operating costs. Meanwhile, the scale down reactor are smaller, cheaper, and easier to handle. Scale up reactor also have higher risk of failure because it involve a large amount of material. On the other hand, scale down reactor are safer for experiments and process improvement. Lastly, modifying the process in scale up reactor usually take more time, while changes can be done more quickly in scale down reactor. So, which reactor is the best choice? In my opinion, scale down reactor are more practical during the research and the development stage because the problem can be detected early without wasting too much material, time and cost. However, scale up reactor are still very important when the process is fully optimized and the product is ready for commercial or large scale production.